Hello, linear algebra student. This video is for chapter 1.7, part 2, continuing with the discussion on linear, dependent, and independent. So we have a theorem called Theorem 7, saying that if inside a set of vectors, if one vectors is a linear combination of the others, then the whole set is dependent, because you can actually just set out a equation where you have some non-zero number that combine all the vector to 0. Say we were actually working on this. Okay, example, we have 3 vector 1 0 0 0 1 0, very easy. 0 2 0. Obviously you can see that vector 2 is 2 times of vector 3 is 2 times of vector 1 vector 2, right? Times 2 is 0 2 0. So you can by the definition of linear dependent, you can say 0 times v1, which is 1 0 0. We don't need it. And then plus 2 times of v2, which is 0 1 0, plus a negative 1 of v3, which is because you can say 0 is equal to 2v2 minus v3, right? Or the other way around. You can say minus v3, which is 0 2 0, and it's equal to 0. There, I have a set of linear combination of the 3 vector, although one of them is 0, and so that's why it's dependent. And even if we don't want to use the definition, you can say if one vector is a linear combination of the other, then it is linear dependent. So you can use this theorem or theorem 7. You can use this and I say theorem 7 say that if one is the linear a combination of the other one, doesn't have to be all of them, just some of them, then they are dependent. And this show it too. So I want to emphasize that you don't have to have all the vector being a linear combination of the other. So long as you have one, that's fine. Because so long as you have one solution that is non-zero, that is would classify that set as dependent. For example, V1 is not a linear combination of the other vector. Obviously, V1 you cannot have 0, 1, 0, x1. So if you try, plus x2, 0 2 0 equal to 1 0 0 is not possible, right? No solution. Okay, so we can try. You can just obviously say that this is x1 times plus 0, x2 plus 0 equal to 1 is not possible, no solution. But you can actually use the a vector, use a equation to try. So it's 0 1 0, 0 1, a new row, 0 0 2, 0 2 0 0 plus a column, which is 1 0 0 is our v1. We want to see if it is equal to v1, and then we do a row echelon form of f. This is f, right? So you can see that it is a no solution, right? Because it's a contradiction. So that is 1 2 0 0 0 1. No solution, because that is equal to 1 0 0 0 0 1 0 0 0. This is a contradiction. Zero equal to 1. Okay, so that's how we do it. So you can use linear combination concept to determine if a set is linear independent or not. So there's another, so instead of doing things, another theorem, theorem 8. Theorem 8 said that also it is also useful. If we have more vector than their entries in each vectors, then the set must be linear dependent. right? So kind of like this, I have a lot of vectors, 1, 2, 3, 4, 5 vectors, but I only have 3 rows. So obviously this must be linear dependent. Why? You must have some free variable or maybe no solution, right? So if you want to add them equal to 0, 0, yeah, for 0, 0, 0, there's no such thing as no solution because you can even if these are all 0, it's you always have a solution. So the worst case would be all of these are like prefix columns, or you have 3 prefix columns only, right? You cannot have more than 3 prefix column. So it must be linear dependent. You must have 3 variables, right? So 3 variable exists. And there's no such case of no solution because in your augmented matrix, you are solving for 0, so they always work. V variable always exist. And those variable will give you a way to write a linear combination of some vector versus the other. So for example, I don't have to actually check with a row echelon form that these are linear dependent. Why? Because I have 3 vectors and it's greater than 2 rows. So must be dependent. Then you might ask Ms. Chen if they are multiple of each other. If they are the same of each other? If they're the same, you don't take them away. They are still vectors, so you can actually put them write a relationship between them. Okay. And of course, if the one of the vector is 0, 0, 0, that must be dependent. Why? Because I can, so like this one. So let's go from top. So let's go look at theorem 9 first. Theorem 9 said that, yeah, if the list of vector contain the 0 vector, then it must be linear dependent. Why? Just imagine if I have a vector like 1, 1, 0, and then 0, 0, 0, and then 1, 2, 3, whatever that I want. It is dependent. Why? I don't have to check because I can just say 0 of 1, 1, 0. Plus, you can give anything to the 0 vector like 5 of 0, 0, 0, and then zeros. Force all the other one to be 0, but one of them to be non-zero, then they are 0, right? So you can solve it with a non-zero weights. So they must be dependent. So that's the definition of dependence. Okay, so with theorem 7, which is linear combination, and 2 vector situation, and checking 3 vector situation, and also the number of columns, number of row. You can actually check your vectors are linear dependent or not by inspection. Okay, so there is 4 of them. I have 3 columns, must be dependence because I have 4 vectors is greater than 3 columns, 3 rows, right? Must be dependent because the maximum pivot column I have is 3, and there must be 1 variable. So 0 is in the list. So must be dependent, this is theorem 9, right? Theorem 9 said that if it contains a 0 vector, then. And the last one is 2 vectors, so check if they're multiple. Are they multiple of each other? If I times v1, let's say this is v1, times 3 over 2, like I divided by 2, and then times 3, you'll see that it is, no, negative 3 over 2, right? So the ratio between them are exactly the same, is always 3 over 2, 3 over 2, 3 over 2. So v1 is v1 times 3 over 2 plus v2 must be 0, right? Negative, positive. If I multiply it and then add the v2, so this would be 3. This is 6. This was 6. This is 9. This is 15, and Oh, I think this is negative, otherwise it's not working. So this must be negative, otherwise they're not. So they are dependent because they are multiple of each other. Yeah, otherwise they're not. Okay, then they would be independent. So dude, so this is finding dependent and independent. Do not use REF, but by inspection using theorem 7, 8, 9. So get familiarized with these three theorems. Okay, see if they're a linear combination of the other, see if it has a zero vector, see if it's two vector, one is the multiple of the other one, and then the size of the column and the vectors. Now, let's look at some more advanced topics. So this is about unknown. So you have three vectors. So if I want these three vectors to be linear dependent means I can add them together equal to 0, and it is a um, three I have three columns, so what should H be? So let's look at the situation. So look at this V1 and V2, V1 times 3, right? If I multiply by 3, that's exactly the opposite of V2, right? And I plus V2 is already equal to 0. So actually, without worrying about V3 at all, so I have 3V1, right? This would be 6. And I add V3 at V2, and I would just multiply 0 to V3, just label them as V1, V2, V3. It is already equal to 0 for all value of H. I don't care what H is, it could be anything because I don't really need this to get this weights. So the set must be dependent for any value of H. You can also do row reduced echelon form to discuss it too. Okay, so let's do the second one. Do we see multiple of each other? Okay, if not, then we would actually just do the row operation, right? So row 1 times 2 plus row 2, put it back into row 2. So that means 4, negative 12, 16, negative 4, 7, H will be 2, negative 6, 8, negative 4, no, I have to do it. So it'll be 0, 5, negative 5, and 16 plus H. And then the next one is divided by negative 2. 2 R1 divided by negative 1 half plus R3, right? Put back into R3. So negative 1 half will be negative 1, 3. Negative divided by negative 2 is negative 4. And then I have 1, 3, 4. Okay, so it's, well, I should have a 0, 0, 0 also. I should do that because I'm trying to solve x1 v1 plus x2 v2 plus x3 v3 equal to 0. So so I would have 0, 0. The 3 is the 3. Is it 6? Oh, 6. I thought it's 3. Okay, 0 and a 0. So when would I have solution? So you can see that I have, I can get rid of this by adding this with this. That's kind of difficult. So, well, actually, I can just divide this by 6, right? So become divide this by 6 and multiply. So negative 6, 0, 0, negative 5, 16 plus H, 0, and then this become just 5, 0, 0. So R3 times 5 over 6. And then the next one would be get rid of this 0, will be R2 plus R3, put into R3, and I would have 2, negative 6, x 0, 0, negative 5, 16 plus h, 0, 0, 0, 0, 0. So this always have a, I have a solution, right?